So this video is a literal copy of the high-level video, except for the calculations are removed, and just this very first slide. So the very first slide is just the overview. So increasing valent electron shells going down, if I can find my pen, going down the group. Therefore, removing an electron is very much easier because it is further away from the positive nucleus. And the general overview of a cross is it is the same shell, same distance from the nucleus, but the nuclear charge is increasing. Therefore, it gets harder and harder to remove the electron. So the ionization increases across and decreases down. So please watch the rest of the video. I have just slightly altered it to take out the high level stuff. Now, just as a quick recap, we remember that when we have the electron excited too far, that it will just disappear, and so that's the ionization energy. So the atom becomes an ion because it's lost an electron, and it's when all these the lines stop, so we know that the wavelength is here. That's when you've added too much energy and it won't come back and it heads off into space. And so the actual definition you need to know. The definition, it's better to be able to write this out because this also gives you a good definition if it's written out correctly. And so as it's a formula, these represent 1 mole. So it's 1 mole of atoms converted to 1 mole of ions by removing 1 mole of electrons, and it's in the gaseous phase. All right, so the energy required to remove 1 mole of electrons from 1 mole of atoms or ions in the gaseous phase is the first ionization energy. So make sure you can write that out exactly and read it off as a definition. So we need to be able to explain this full diagram here. And there's 4 things we need to note. So the first trend we're going to do is the group trend. So if you look down group 1, hydrogen, lithium, sodium, look down the first group, you'll see that it's just these ones here, and you could look down one of the other groups if you wish, and you can see it's generally decreasing. Okay, and so that is because they're in larger shells. Now, next unit topic, I'll talk about this a little bit more. That actually should be slightly larger. So there's a conflict. It's also a larger nuclear attraction, but it's a greater distance, and you'll see from a balloon demonstration again, the distance is exponentially more important than size of charge. So the force of something is it's always much, much greater. So the effect of the distance is much, much greater than the effect of increasing the force. And so what you effectively have is, as you go down, it's easier to remove the electron because the effective nuclear charge is decreased. There's also increased nuclear shielding. So that's avoiding the attraction between the negative and the positive. Okay, so for that reason, it is easier and easier as you go down a group to remove an electron. So the first ionization energy decreases. So the periodic trend is a little simpler. The general trend is it's getting harder and harder. That's easy because they're all in the same shell, so they're all the same distance around the nucleus, but the nuclear charge is increasing as you go across the period. And so, of course, it's harder and harder to remove the first electron from an element as you go across. So ionization energy increases across a period. Now, the shells also, which we've talked about before, these large jumps are because this is in one shell and they're a lot harder to remove. But when you jump to another shell, it's a long, long way away with only 1 proton increase, but a huge distance increase, and so it's much, much easier. So they indicate the shells, these large jumps, the energy levels. Now, we're just going to do the 2 exceptions as well. And so you can see that this one slightly decreases. And that's because we have here, it is a lot easier to remove an electron from this because it's in a new subshell. Not a complete shell, but a new subshell. And so there's also a little bit of electron shielding. And so this is closer to the nucleus, so it has a slightly stronger pull to it. This is slightly further away from the nucleus, so it's slightly easier, so that's why it drops. And the other 2 exceptions are these ones, and these ones are halfway through the P's. And so they are the same distance, but we have their mutual repulsion, so it's easier to remove electron from the oxygen and the sulfur here because of the mutual repulsion effect.